for instance, like the switching equipment cost and the operative expenditures regarding the costs. And one approach for doing this is thinking how do we connect the users to the provider. And a way of doing this is taking into account how do we cluster these users. And in that sense, it's been demonstrated this is the most optimal way of doing this, going from the central office with a long optical fiber, which is the feeder fiber, up to a remote node, which is a switching equipment usually in LUBG, which is a multiplexer, demultiplexer for wavelengths, and then going to the final users. Here we are in the central office. Here we are in equipment called optical line terminal, and in the users we have equipment called optical network units. So the extended star topology is the most efficient way of going there to the users. But the question remaining there is how do we cluster the users in order to do this thing? So the optimization problem related with that situation, it's an unresolved problem actually. So this paper proposes a novel methodology for doing the optimization of the implementation of passive optical networks based on something called Voronoi partitions, and particularly a Delaunay triangulation, because the Delaunay triangulation is very interesting because the Delaunay triangulation has the property that the Euclidean minimum spanning tree is a subset of this Delaunay triangulation. So if we take into account the following sets of variables, the optical network terminal, which is only one element there, the optical network units, the available switching equipment, and the candidate sites for placing such available switching equipment. And then also we take into account some other variables like the variables taking into account if a link is active or not, if that link belongs to a specific route or not, the Euclidean distance between two sites, and the if in a candidate site is it placed a switching equipment or not. Also, we take into account some parameters like the fiber optical fiber cost, the capacity of the switching equipment, the optical fiber attenuation, the loss in the switching equipment, and the power budget in the system. So the optimization problem related to that is minimizing the cost, which is in the end the cost of the optical fiber plus the cost of the switching equipment, subject to the following restrictions. First, the first restriction should be if you're in the provider's headquarters, you need only one link connecting to some specific switching equipment. And also, if you're a user, you need only one link for connecting to your equipment. Also, if you have one candidate site, you should place there at the most one switching equipment. It's not efficient putting 2 or 3 switching equipment there. And switching equipment should connect at least two links, one inside and one outside link at least. Of course, usually more than 2. And the switching equipment there should provide a capacity at a